This is tutorial 3 of chapter 5 of the Digital Soil Mineralogy with R course, and in this tutorial we're going to be comparing the diffraction data from Scotland with that from Mars that we've manipulated to be comparable from the initial form where they were recorded on instruments with different X-ray sources and at different X-ray at different resolutions. So to do this comparison, we're going to write a function because this function needs to be applied to thousands of comparisons. It's by far the most efficient way to do it. So our function is going to firstly align the two samples that we're comparing to one another, because there are potentially small differences in the peak positions associated with sample displacement that we've covered in previous chapters that we can account for. So we're going to try and align the samples to one another, and where there are similarities between the samples, that will produce a better correlation coefficient. So we're going to firstly do that alignment using the align xy function, and we're going to create a multi-xy object from a Martian sample and a Scottish sample. So these are both xy diffractograms. And we're going to treat the Mars sample as the standard. Doesn't matter which way around you do this, because you'll end up basically with the same results. We're just aligning the two samples to one another. So in this case, the Scotland sample will be shifted in order to get it to align with the Mars sample. We're going to specify one of our arguments in the function to be align, which will be just a simple numeric value that allows the Scotland sample to shift either positively or negative by on the 2 theta axis. So we set it to a small value like 0.2 degrees 2 theta. The align xy function takes a couple more arguments, the xmin and xmax, which define the 2 theta range upon which the alignment is carried out, and we're just going to use the minimum of the 2 theta axis of the Mars sample. So once it's aligned, the function is then going to calculate the Pearson correlation coefficient, just simply using the count intensity of the Mars data. So we're accessing that second column there, and the count intensity of the Scotland data. And that will, by default, the core function derives the Pearson correlation coefficient. And then we'll make sure that our function returns that correlation coefficient. So each time it runs, it creates that numeric value. So that's going to be our function, which we'll just load into our environment here. So we now have this compare XRPD function, which accepts the arguments Mars, Scotland, and align. Now we can simply apply this function to a Martian sample by using the supply function. So the scenario here is that we're going to take one Martian sample and compare it to all 703 samples, or 703 samples within the Scotland XRPD dataset. So we're going to take that Scotland XRPD dataset, we're going to use the compare XRPD function. We're going to set the Martian sample to be the Cumberland sample in this case, and we're going to set the align to 0.3. So the Scottish sample will be able to shift by that amount in order to get the alignment to optimize. So because supply will recognize that we haven't provided the Scotland argument to our function, so it will infer that we're going to apply our function to each item within this list. So if we run this, it's going to run our compare XRPD function 703 times to derive our Pearson correlation coefficient. So that will take, I don't know, a minute or so to run. But once it has run, you'll end up with this Cumberland to Scotland vector, which is a named numeric vector of 703 values. So if we look at the head of it, so the first 6 values, we can see that we've got 6 values, each named according to the IDs in the Scotland, or the names of the XY um, objects within our diffraction data. So we've got the first 6 names there, and the numeric value specified in each of these items within the vector is the Pearson correlation coefficient of this Scottish sample to the Cumberland Martian sample. So here they're all pretty low, ranging from about 0.8 to 0.18. Okay, but we have another 700 or so values within that vector. Now that comparison is just for one Martian sample, but we want to do it for 31 samples. So to keep things simple, we're just going to do what we've just done, but in a loop, in order to get all 31 samples correlated. So that loop is going to populate something called Mars to Scotland, which is going to be a blank list to begin with. So we've got Mars to Scotland, which is a list of 0. And then we're going to run this loop 31 times. So we're going to run it from 1 to the length of the Mars XRPD data, which is just simply a vector of 1 through to 31. And so the first time it runs, it's going to populate a first item within our Mars to Scotland list, and it's going to do the supply of our compare XRPD function, just like we've done here, but it's going to use the first item of the Mars XRPD data in the first time it runs, and then in the second iteration it'll use the second item, and so on. And it will work its way through all 31 samples. And in the loop, we're also just going to make sure that the name of the item within the list that it creates has the same name as the names of the sites that are provided in the Mars XRPD data. So in the first iteration of the loop, it will make sure that the item of the list is called Rock Nest 4. So if we run this loop, again, it's going to take a few minutes to run, because we're doing so many comparisons. It's doing 700 alignments and correlations each time it runs, and it's running 31 times. So it's doing like 22,000 of these alignments. So I'll just set it off running and pause the recording and then start again once it's finished. And so that's finished running after 20 minutes or so. So we can have a look at our Mars to Scotland list that we've created. It's a list of 31 objects. Each one of them is just a numeric vector of 703 values. And each of the objects within the list is named according to the site on Mars. What we can do to this list is actually unlist it to create one big vector using unlist. So if we create a Mars to Scotland vector, V, using this unlist, we'll end up with this large numeric within our values part of the environment. And this is a very long vector of about 22,000 correlation coefficients. If we look at the first value of the vector, or we could look at the first 6 values using head, we can see that each value has a name. So it's a named vector. And the name takes the form of the Martian site name firstly, followed by a full stop, and then subsequently the unique ID of the Scottish diffraction sample, or the Scottish soil sample. And so that takes the form, same form for all of these correlation coefficients. So we could actually use this information to actually compare two patterns to see how they how they look. And to do that, we'll actually need to do the alignment just to make sure that we're going to plot what the correlation coefficient was derived from. So for example, if we wanted to plot the data used for this comparison here, we need the Rocknest 4 sample from the Mars XRPD data and sample 891338 from the Scotland data. So we'll create a multi-XY object from that, and then we'll do the same alignment routine as we did within our compare XRPD function. So that will just produce aligned data of those two samples. So we've got those two samples within a list now, or a multi-XY object, and we could just simply plot that. Using the same plotting form as we've already used numerous times. And we'll have this, yes, a comparison of those two samples. So we've got our Rocknest 4 sample plotted against this sample, which just happens to be the first out of all of the comparisons. So yeah, pretty much no similarity there for this data, but that's not surprising given that it's got a pretty low correlation coefficient of about 0.1. But we can have a look at our vector and summarize it just to see whether this is unusual within the dataset. So producing a summary tells us that the correlation coefficients range from minus 0.2 to 0. Plus 0.8 with a mean of about 0.16, 0.17. So that shows us that there are potentially some values that do have quite a high correlation coefficient, and we can further explore this summary data using a histogram. So we're just going to create a histogram, a ggplot2 histogram here of the data. So we're just going to create a data frame because ggplot2 won't accept vectors like we've got. We're going to create a data frame with it where it's just got one column, and that column is called Pearson, and then we're going to set that Pearson column to be the x-axis, and then we're going to create a histogram and provide a couple of labels for it. So that will produce a histogram with 100 bins, and this is our distribution of Pearson correlation coefficients. So we can see it's approximately normal, really, but we do have a slight right tail to the right, where we've got a few samples that have correlation coefficients around 0.75, 0.8. So that's quite interesting because it seems to be a distinct tail of samples there, and it might hint at the fact that there are some soils within the Scottish dataset that do correlate with some of the Martian samples. So we're going to further explore this region of the histogram by just extracting the data within this vector that are greater than 0.75. So we're going to create something called high cores, which is going to take that vector of 22,000 coefficients and just select the values that are equal to or greater than 0.75. So we now have high cores, so there aren't that many of them. There's a range of different sites included within this vector. We've got Cumberland is coming out as quite high in a few cases, John Klein, Lubango, Marimba, and so on. So there are a few sites that could probably be explored in a little bit more detail, and we can access the site names using this subroutine where we're just going to access the names preceding this full stop. So if we run this, you'll see that this function call just extracts all the Martian site names. So it's using that full stop as the separator. So we'll create a high cores Mars, and we'll look at the unique sites that are included within that. So we can see we've got, about 12 sites whereby there are correlation coefficients greater than 0.75. And we can do the same or the opposite for Scotland, where we're going to extract all of these unique identifiers. So running that just extracts everything after the full stop. So that creates something called high cause Scotland, and we can look at the unique values there. So in this case, we see that we actually only have 7 unique soil samples where the correlation coefficient is greater than 0.75. So quite a restricted set compared to the 700 or so that we supplied to the comparison. And now we'll have a look at do the same thing, but we're going to actually extract the highest value. So on this right hand side, we're just extracting the highest correlation coefficient. So, and the name of that correlation coefficient. So we find that the highest value is the comparison between the Cumberland sample from Mars and this sample from Scotland, 926674. So we're going to extract that, and we're going to also extract the IDs of the samples that correlate to Cumberland. So we're going to extract these 3 samples. So just to explore the data, there are lots of different ways in which you could explore all these relationships, because there are quite a few identified from this analysis. But here we're just going to keep things simple by looking at the Cumberland site and the samples that correlate most highly to it. So we're going to create a multi-XY object from this Cumberland site. So we're extracting the Cumberland site here, and we're extracting these 3 samples from the Scotland X-ray powder diffraction set, and we're just creating a multi-XY object from those. So if we look at our Mars highest core data, it's a list of 4, where we've got Cumberland as the first sample, followed by those three samples that correlate highly with Cumberland. So now we're just going to do one final thing before we plot those comparisons, in that we need to align the data again, just to make sure that we get the best possible comparison. So we're just going to align all of the samples within this list we've just created to the Cumberland site, and then we're going to plot it. And I'll plot it again just by changing interactive to true so we can get a better look at it. So we should be able to see that compared to that first comparison that we plotted, where we had a pretty low correlation coefficient of 0.12 or so, these are looking far more similar. So if we just restrict it to Cumberland and perhaps to one of the samples, just for simplicity here, we can see that we have the 2 signals. The red line is the Cumberland sample, and the blue line is sample 926674 from Scotland. And in general, the similarity is quite striking. There are many peaks in the correct positions, if you like, and their intensities do differ in some ways, but are similar in others. Interestingly, there's this clay mineral peak at about 15 angstroms, which seems to center in a similar location. So that could be an indication that similar clay minerals are present within these samples, which is of particular interest because they are very challenging to study using a rover on a distant planet. So that's quite encouraging to see, and the other parts of the mineral composition are quite similar in many respects. So that's an example of how this data-driven approach can be used to identify samples on Earth that might have similar mineral compositions to those observed on Mars, both by direct measurement with diffraction data. And as one final piece of the puzzle, we'll actually just have a quick look at the location of these samples. So of these 3 samples that we've got that we just compared to Cumberland, if we just have a look at where they're located in Scotland, just using a quick leaflet map, we can see that they're both located on the west coast. And we've got one sample located on the Isle of Ulva, just to the west of the Isle of Mull. And we've also got one site, sorry. That's one site where I think potentially a couple of samples are from. And we've also got another site here on the Isle of Skye, on the Trotternish Peninsula. And both of these areas, or both of these locations, contain soils developed from basaltic parent material, and that's the same parent material as is understood to be present on Mars. It's very common soil parent material, but perhaps the conditions of high rainfall and temperate climate on the west coast of Scotland here has resulted in conditions for that parent material to be altered in a similar way to it once was on Mars, to form those clay minerals and that peak at around 15 angstroms that we've been able to see in the data. So there's lots of ways you could explore this comparison further, but the idea behind this whole chapter and tutorial was just to use it as an example to show how data from different instruments, even if they're on different planets, can be compared to produce hopefully meaningful results.